I'm talking about on GIS application in mineral exploration, just the basic in the presentation of GIS. Some of the times that one actually needs to know. I'm not an expert in that, but I think I've practically used some of those things, and I will share some practical examples how some of these things have actually benefited us in mineral exploration. In Dick's presentation, we'll try to look at overview of GIS development in the development of minerals, and some practical experiences, that one can actually use in ArcGIS, and also some implementations of GIS projects. Then running through that, we'll look at what is GIS, what can it do for us, what is the organization of GIS, then what is GIS infrastructures and the principles. We'll look at the spatial data representation, the vector and the raster data model, the advantage and disadvantages, the sources of our data, and we try to maybe explore some GIS environment and see how it goes. As a matter of introduction, as we've just said, GIS, as the name implies, is geographic information system. When we're talking about geographic, we are referring to a location, talking about the real world coordinates. There are different coordinate systems one can actually apply in GIS, depending on area where you're working. There are also some projected kind of system, and there is a local dotum kind of system, and there is geographic in the sense that we talk about the WGX 84 and all that. When we're talking about the information, we are referring to the database that actually involve, then the system itself involves the hardware and the software. You cannot actually do without it. So GIS, most of the time it's using is a multidisciplinary kind of a package. It depends on where you want to use yours. Which profession are you involved in? You can't come up to say you're an expert in military GIS, you're an expert in criminology, you are in transportation, you are an order. But I think one can actually try to look at, there are so many tools that are actually involved in GIS. So you look at what suits you best. If you are into water, you can specialize on that of water. You are into environment assessments, you can specialize in that also. So it is a multidisciplinary tool that can help one to actually get some problem, some data stored, queried, and analyzed. Okay, the concept of GIS is just based on data layering, data integration, and coverages. This is just what it looks like in a conceptual view. So when you're talking about the GIS, look at this land use, the street and the district parcels. All can be integrated together on, being superimposed on a land. Talking about if you're a soil scientist, you can make use of a particular portion of land and define the street on that particular location, the houses on that location, whether there are drainages on that location. If you're a geologist, you're interested in the rock and all that, you can also mark these particular areas based on your rock types and all that. So you see, it's all about an integration and bringing out a particular kind of data one might be actually interested in. Then we say, what can GIS actually do for us? GIS does a kind of 5 to 6 functions. These are fundamental things the GIS can actually do. We can use it to capture data through different sources of GIS. You can store data with it, store your data, and data you store are retrievable. You can query your data. You can ask so much questions, some of the complex questions based on their attributes. To query your data, you can analyze your data. Also, you can integrate all this data into multiple sets of data sets find features that meet up a specific kind of criteria, and bring out your analysis. And at the end of the day, you'll be able to display your data in such a way that you might want your audience to understand your data, or in such a way you want to bring out your special thoughts concerning your data, and you actually present them in terms of high quality maps, in terms of graphs, in terms of reports, and every other format you might actually want to do. Okay, we'll look at some organizations of GIS data. There are so many kind of data formats and varieties that could be found in GIS. But this is very important one we actually see on our day-to-day GIS work. Most of the time we talk about the shapefiles. It's a simple non-topological format for storing geometric locations and some attribute informations. Most of the time it ends with .shp. The essence of knowing these strings is to enable us understand a particular kind of data whenever we are looking for data. So if we are looking for a shapefile, every shapefile data is stored with this string.shp. Another one, very important, is the @info data. This is also known as @grid, as a raster file format developed by Esri to contain some information about geographic space in a grid. We'll talk about the DBS, which is, whenever you see it, is the database data kind of format. Then this DXF, the AutoCAD, is very, very popular. The file extension is actually for AutoCAD graphics, images. Then we look at the TIFF. TIFF is also most of what we use for tagged image file formats. It's abbreviated as GeoTIFF also. So in DIX, whenever you store data in DIX, it stores even the XY coordinates in an image format. So you don't need any kind of georeferencing or possibly another kind of projection when you save your data in TIFF format. And .gpx is also another type of string we can see in data. Is actually for GPX, like our presenter today has actually talked so much on GPX. So this is another way we can store some of our tracks, some of our waypoints we see in the field. The essence of this is for us to understand there are particular software in GIS, whenever you are trying to correlate or you're trying to make use of, you're trying to change your data from one format to the other, or you are trying to bring in some data, the essence of knowing some of these strings is for us to know that this particular software can accept data in this format and in the other. Then we'll have the CSV, the ASCII files, and the text files, and with other digital formats. Again, we'll look at the infrastructures whenever we're talking about the GIS. The infrastructures are we can't do the GIS without the hardware. The hardware, we can't do it without the software. We can't do it without the data. We can't do it without the organization. When we're talking about the software, the hardware, we're talking about the computer itself. We're talking about the software. We're talking about the ArcGIS application itself. There are varieties of GIS softwares. The most popular ones are the ArcGIS. We'll have the ArcInfo, Map Info, we'll have the Global Mapper, we'll have the name them. There are so many of them. We'll have the QGIS in the market. So we'll talk about the data. The data is part of the GIS infrastructure. You cannot have a software, the hardware without the data. The data is everything. It's the information you are going to analyze. How good your data is. It's actually how good your result will be. What you put into the software is what comes out. So most of the time, our young geology would think that once we put in data, the GIS will just analyze and bring out everything and all that for you. You predict. It's just like going into a vehicle and you want to drive. When you are driving, it's the destination you are turning your steering to that you find yourself. The car doesn't take you to a destination when you don't turn your steering. And this is where I made this mistake. Practical. If Patricia, okay, Patricia is not If Patricia is here, I don't know whether she was among of us that got trained in one of these computer applications some years then, in Minex. There's a particular mistake we did when we were being trained in Minex. You know, what happened was, you know, we were given data to work on. It's a project that even still alive till today. It was a very big project. After being trained, we are asked to practice what we are trained on. So we are 5 of us, 2 mining engineers and 3 geologists. And I was one that is supervising the whole thing. So what happened was we queued in the data into the application and we started modeling and all that. We forgot to tell the application that, you know, that whatever we are modeling is restricted to a particular crop line. Just a single mistake, it will call it kind of a subcrop line, because we are looking at a subcrop line that we do not see. When I'm talking about subcrop line, we're talking about a crop line that is beneath possibly some covers of about, say, 6 meters or 5 meters or thereabout. And we did all the model, and we never brought in a subcrop line, which the system will use in terms of resource estimation and resource calculations. So we calculated, and we have over calculations, you know, and during presentations, it was disastrous. It's just because if it was not actually found, then the management was already happy. They were already happy that we are having a very interesting numbers, until our supervisor that came in there started asking some critical questions. You know, the numbers that we are bringing out was something that we're not actually tallying with what's supposed to be on the ground. But, you know, as we are very excited and we're very excited and happy that we could do it. You know, that we could operate the system, the software and the application. But we never knew that whatever you give the software is like Mumu. You give him anything and he doesn't even ask you 1 or 2, he just bring it out for you. So there's been so much one need to do. That's why the way you process your data is very, very important. It's just like what we are talking about, mapping some alterations or mapping this and that, even structures. And I've seen so many people just drawing lines on the magnetic maps, you know, aeromagnetic data, drawing line, everything is line and all that, and they call it lineament and structures and all that. When you get to the field, you will not see anything that looks like that at all. Even if you go down to 100 kilometers, you won't see anything like that. So I think that your data processing and is very, very important in GIS. Another one is the organization we are talking here and the people. It's very important. You know, you need to have organized people, and it requires the right people, you know, to give you actually what you want. Then we'll talk about the principles of GIS. We won't actually say much, but the principle of GIS, you know, it has a very unique one, which allows us to abstract some information from the physical world and display them in layouts or themes. That is just what GIS is all about. Whatever we think we have in the real world, how can we put it in layouts and be able to, you know, bring all of them in one particular one particular environment, so that we can actually see them side by side and start making decisions, you know. Now, each layer depends on how you're able to process it, how good you're able to process it, the resolutions, the experiences. A lot of things are involved in a layer. So any layer counts. And at the end of the day, what are you looking at? You are looking at a coincidence or a kind of a particular interpretation that gives right to what they are looking for. So if you are looking for a particular mineral, you should be able to understand the ore, you know, behavior. What is the attitude? What is the genetics? How do they form and all that? Are you now telling, you need to mark, are you now marking the structures as number 1? Are you marking the geochemistry data as number 2? What weights are you giving to each one you want to use? You know, so this is the main text. You know, it can convert data between different data models, into another models, and unlike most of other databases and statistical software, So that exists. Then we look at the spatial data. In GIS, two things are very, very important. Any kind of data you are bringing in GIS mostly fall within. Data must have X, Y, or Z. We're supposed to be able to pinpoint it on the real world that displays this data is coming from this particular location. It doesn't need to float anywhere. So you need to align. That's why when you're bringing anything in a GIS environment, all of them must be in the same coordinate system. You can't be working in UTM and be working in WGM, working in the grids at the same time. It's impossible. So they must align. So when we are talking about spatial data, there are two data formats. We're talking about the vector model data and the raster data. The raster data are the one that has a specific, most of the time you're talking about the points, your lines, and the polygon. The vector data is structured with two specific kind of elements, the vertex and your coordinates. While your raster data, when you're talking about your data, is a data that actually represents an area or region as a suffix. And this one actually is a kind of continuous kind of data that is divided into grids of cells. Raster data goes beyond the point, the line, polygons, and they represent by a grid of cells and can be measured in terms of resolutions. So the raster model data are continuous, while that of the vector data discrete kind of data. We'll look at trying to see, okay, if you look at this, we can see that this is a vector data. Vector data is when there is a point data. You can see this. It has only the X and the Y. From the point data, you can actually graduate to line. You can see line here. Line is also a vector kind of data model. Line, the point gives you up to line, and from this line, you move into a polygon. Here you can see a polygon is an area that's fully encompassed by a kind of a series of connected lines. So this is an example of vector data. Then we look at raster. Rasters are actually data that are continuous, actually done. You see them in, in grids which actually connected by columns and rows in XY. So the grids of raster depends on a resolution. If you look at this, for example, it's 5 by 5 and all that. A grid of 1 meter by 1 meter is better than a grid of 2 meter by 2 meter in terms of resolution. The same way it goes better than 5 by 5 or 10 by 10 and all that. Resolution of any image depends on what you are looking for. That is just it. I was listening to when we were talking about GPS resolution. Other presenters, we have a new technologies of GNSS now that can pick accurately and resolve so many things to even 0.001 or 0.1 or the case may be. But at geologics in regional sense and all that, trying to look at, because the more resolution you try to zoom in, the more costly it becomes. It becomes costlier, it becomes heavier, graphics increasing, so many things increasing. So the main thing here is looking at what you want to do. It has to be specific to, if I'm looking at a regional trend or certain things, I don't need the GPS that can give me 0.1 or whatever and all that. If I'm trying to pinpoint a vein that is as big as 100 meters, I don't need all those kind of resolution. But if I'm trying to look at, I will even try to look at resolution very critically when it comes to maybe I'm trying to look at my overburden kind of what I actually want to do. We'll look at these two data. They have some advantages like what I've just said and disadvantages. Raster data model is actually simple in terms of structure. And when you talk about vector data can be, represented in its original resolution without even generalization. They require less disk storage space, unlike the raster data. And topologically, relationships are really maintained in that. You don't easily actually see changes when it comes to that. Then the same thing here, there are disadvantages. Vectors are very, very more complex data in terms of structures. But most of the disadvantage of raster data is graphics. These days, we know that whenever you are using systems that do not have dedicated graphic cards, you might not be able to upload some raster data, even some remote sensing. So that's why you will need some dedicated graphic cards and a very high powerful systems to actually store some of these raster models and be able to process your data. Then to look at some sources. Sources of data whenever we're doing a project is very, very important. Sources of data to GIS environment could be, coming in kind of hard copies. Can come in hard copies, or can come in digital files, formats. Hard copies, the way we scan our data or take a picture of it and digitize, or georeference and digitize, and all that, we can bring it into GIS environment. And also tree imagery, remote sensing imagery, photo imagery, Google Earth, summit imageries can actually be used as a sources, as a way of bringing data into our GIS. Then GPX is one of the most commonest way of bringing data into GIS environment. Then again, can have our data coming into GIS environment in terms of Excel, in terms of text delimited, in terms of DBL files and all that kind of, and also from reports, different reports of so many years, historical reports can actually give us, can give us the sources where we can bring in data. Once again, I still say it is very, very important that we look at our sources very well. The sources of your data is very important. That's why whenever you are doing a project, you want to bring in data to make some analysis and all that, understand the sources, understand the origin, understand the resolution of any data you are bringing in, so that you'll be able to authenticate your results.